So like I was saying, today I'm going to talk about plane geometries. Now, we've all studied geometry right from high school, right from our fifth standard or something. And this is something we have experience with, right? As we keep studying more and more, we start seeing different facets of this geometry. We start learning a little bit of the history of the subject of plane geometry. So what are plane geometries, right? So if I just ask you to close your eyes and imagine, just think about, close your eyes and think about the term plane geometries. The first picture that should come to mind is what we have already studied, namely the planes with its points, lines, notions of incidences between points and lines, and everything that we construct with it, right? So today, let's take sort of a slightly not different, but let's sort of take a step-by-step approach. Let's not delve too much into the history. I'll talk a little bit about it towards the end, and maybe just one word before. But let's sort of try to sort of build from our perception, our intuition, and let's try to see how far we can go. See, for example, again, let me ask a question. So everybody has heard of, how many of you have heard of Euclid's axioms? Click yes. Come up with these axioms and what are these axioms coming from, and so the idea was, I mean, everything comes from perception. See, the way mathematics develops, when people come up with a definition or when people come up with certain theorems and so on and so forth, it's not like a mathematician wakes up in the morning and says that today I'm going to make this definition or today I'm going to prove this theorem, right? It comes from experience. It comes from looking at various examples. It comes from observation. So as mathematicians, we tend to look at everything around us, try to see what the common patterns are, and we try to codify these common patterns, right? So that's how these axioms also develop. Okay. So let's try to sort of take that approach. So before we proceed, I just want to say that this is going to be the reference for today's talk. An Expedition to Geometry by Professors Kumaresan and Santana. This is the book. I would highly recommend that you read it. So this is also, I think, for those of you who are fans of Lord of the Rings, you should see this is the one book to rule them all. At least for me, to understand geometry, because this is already my second talk using this book, and I can probably give 20 more talks just using this book, at least, if not a full semester course. So I would highly recommend that you take a look at this. Everything that I'm going to talk about is there in this book, plus a lot more. Okay. Right. So what is the first picture that is invoked? If I say, so like I said, a plane geometry has two ingredients, right? So a plane geometry has two ingredients. The first thing is we have a non-empty set X. Okay. This we think of as the set of points. Yeah. And we have a collection of subsets. So I hope. So how many of you are here? Are you familiar with this notation? This is the power set. Say no if you've not heard of it before. Okay. So this, if you've not heard of it, this is just a set of all subsets. Okay. So this guy is just a set of all subsets. This is just your set. I take all A such that A is a subset of X. Okay. So we have this special collection of subsets of X, which we think of as the set of lines. And then we have some notion of incidence, right? A priori, that is all we have. We can tell if a point lies on a line or a line passes through a point. Okay. So we just say we have this notion of incidence, right? That is, we say that a point lies on a line or a line passes through. Okay. Now again, just close your eyes and try to imagine. Just close your eyes and try to see. I mean, when you think of the plane, you have all these set of lines that you see. And you can see if I have a point, I can draw a line through it, right? And I can say, okay, this point lies on this line or this line lies on this point. So depending on whether you're better friends with the set of, yeah, Fiona.
In the beginning, the set X that you took
Yeah,
together, does it form a plane? Means it's just a set of points?
yes. So see, that is the thing. What do you mean by a plane? Now, when we think of a plane, we think of say x equals r2, right?
Okay.
Yeah. So that is where the word plane comes from.
So
Okay.
it's a plane because in random, if you take set of points, will L be a subset of X?
So again, what you see, this is what. So okay, that's a good point. So see, the confusion is that when you think of the set of lines, you are actually thinking of the lines we draw in the plane, right?
Yes.
Yes. But this is the perspective that I'm taking. So I have the set X. Okay, let's write it down. So traditionally, what do we start with? Ex- our first exposure, right? Our first introduction is if we actually take what we know as the plane. This is R2, right? And what is the set L that I'm going to take? Let's write it.
X, Y such that there exists a T of the type Tx plus 1 minus Ty, something like that.
Something like that. Or another way of saying that. So now see, what is this L? Do you think this is an element of R2? No, I'm taking L to be a subset of R2, right?
Yes.
Special kind of subset. What kind of subset am I taking? So what is this little l going to be? Actually, I should write little l of ABC, where ABC are real numbers. This is the set of all xy such that ax plus by equals c.
Okay.
Yeah.
Yes.
So all the geometry that we learn, the basic ingredient in that geometry is this set X, which we take as R2, and this set of lines, right?
Yes.
Yeah.
Yes.
So now we're trying to see what is so special about the set X R2 and what is so special about the set of lines. Can we do something more with it? Do we have to restrict ourselves to R2 or can we work with more sets? Yeah. So that is what we're trying to do. So now the idea is that let's just try to see if I start with the most basic idea that I have this set of points and this set of lines, what properties do I have and what properties can I extend to other scenarios. Okay. Is the task clear, Fiona?
Yes, sir.
Okay, great. So now you see that a priori, that is all I needed to start with, right? So far, I have not really come to geometry. So far, I have just said, what is the most basic ingredient? The most basic ingredient is that I have a set of points and I have a special collection of subsets, which I call lines, right? Now see, a priori, if I just start with X and some collection of subsets, it may not be interesting, right? I want to sort of replicate what I see in my Euclidean plane, what I see in this situation, right? This is my special situation. This is our, this is our what they say. This is our pehla pyar. This is our first love, right? So I always try to sort of find reflections of my first love in everything new that I see, right? So what properties do we see over here? What is the first thing that comes to mind? Let's start with a blank page. What is the first thing that comes to mind? So if I draw, say if I have 2 points P and Q, close your eyes and just imagine the first. Just close your eyes. I have this given this information to you. What is the first thing that comes to your mind? What is the first picture that you see? So if you have an answer, if you see something, say yes. Abhay, Jayarajan. Abhay, you said yes. Would you like to share your insight? Okay, maybe Shivanand.
Hello.
Yeah, Abhay, go ahead.
The first thing that comes to my mind is how can I join these 2 points?
Okay. And can you join these 2 points?
Yes.
Yes.
So,
So the first thing we learn is that, okay, given any 2 points, I can draw a line passing through these 2 points, right? That is the first thing. That is the most natural thing that we see. You can draw any point, any 2 points anywhere. I can always draw a line passing through these 2 points, any 2 points. Yeah. And I mean, we actually do this even in school, even on paper. In fact, we also, if you think about it, we also do it the other way. If we want to draw a straight line on a piece of paper, what do? We measure something. Say, if we want to draw a straight line at a distance of say 5 centimeters from the margin, what do? We put our ruler there. We measure 5 centimeters from the margin at one place. We measure 5 centimeters from the margin at another place. Then we put our ruler through those 2 points and we draw a line, right? So this is sort of the most basic thing that we use, right? So let's see. Let's say that this is the first property that we want. From this set of points and this collection of lines, this is the first property that we want. We call this A1. Let's put ourselves in Euclid's shoes and see. From our experience, we are developing these axioms. So the first axiom is, given any PQ in X, there exists a line L in this collection, curly L, such that PQ belongs to L. Okay. So this is the first thing that we would like to have. Yeah. Now let's see. Let's look at some other examples. Since Fiona asked the question, let's look at another example. And let's maybe start with an example which is very simple, but you'll tell me if it's interesting or not. So I take the set X to be just the 2 element set 1, 2. Okay. So now can you think of How many of you can think of some collection of subsets? So I want this to be some collection of subsets which satisfies this axiom. It's given any 2 points, I should have a line passing through them. Okay. So again, if you can think of something, please say yes. What collection should I take? Let me ask Viona.
The power set of X itself you can take.
We can always take the power set of X. Yes. But I mean, that again is not very interesting, right? Because that we can do for any set. But that is a good guess. So we can sort of say, okay, we can take L. We can take L to be the power set itself. But if I take the power set, what is, if I give you the point 1 and 2, what is the line that you're going to take? So if I have this point 1 and 2, what is this L that you're going to take? Viona?
1, 2. The set X itself.
The set X itself. Very good.
Any subset collection you take, it should contain X, then it's done.
But what do you mean subset? Okay, any subset collection you take, if it contains X, it's done. So what if I take this guy? I just take one line. Not really doing anything, right? This works, no? So I just want to sort of point out that this pink line that I'm drawing is not really there. Okay, this is just our way of understanding that you can draw a line between these 2 points. But now you see that I can do this, right? If I take my L to be X, then I'm done. It satisfies this first axiom. Yeah. But then how, like, what do I do with this? That's it. I have this one set, I have these and this one line. I can sit and stare at it for the rest of my life. But what do I do with it? At this point, again, go back. What are we trying to do? We already have a notion of plane geometry that we studied in school and so on. So we're trying to replicate things, right? So what can we do to make this more interesting? Like, again, let me just sort of add by saying that this we can do for any non-empty set, right? So for any non-empty set, we can take L to be X. And this satisfies the pair XL satisfies A1. But what is the difference? Again, let's compare this monster that we've defined. Let's compare this with what we have in our Euclidean plane. So now I have these 2 points, P and Q, in this Euclidean plane. And I say somebody tells you, like, okay, I give you this picture. And say Viona comes and says, you know what, I found another point R in the plane. I have this new friend, he also lives in the plane. So where would you like to draw R? In this picture, where can I draw R? anywhere I want, right? R could be here, R could be here, R could be here, R could be here, R could be anywhere. In fact, there is something very special that happens, right? I can always find an R which is not on this line. In the plane, I can always find an R which does not lie on this line. Yeah. But now you look at this example. You look at this example, or let's take something more concrete. I'm sorry, did somebody want to say something? No. So if I look at, say, let me add one more point just to make it a little nicer. And again, I have this L equals X. So I have 3 here and I have 2 here. So say I give you, I know the points 1 and 2 are my friends, and Fiona comes and says that I have this point, a new point. Where can I put this new point? Whatever it is, it has to be on this line, right? Because I have no other options. So this set of lines that I've taken, this collection of lines that I've taken, I've not left it very interesting. Everybody lives on the same street. There is nothing to explore. If I want to have pav bhaji, all of us will have to go to the same place to have pav bhaji. We won't have any choices. But in R2, we have something more. We have many choices. We can explore. We can go to different cities. We can go to different places. We don't have to just walk up and down the same street again and again. Okay. So in R2, what do we have? In R2, in our standard, okay to say standard model, but in our usual model, in our known model, what do we have? We know that there exists PQR here, which are QR are non-collinear. At least this makes our life a little more interesting, because we know that, oh, so if R is over here, I know that, oh, there is more, I have more room to explore. I can draw more interesting pictures. I can do more interesting things, right? I have more room to explore. Yes, Keshav.
In our previous example, what can we like non-collinear can be? Like we just define as that like right now. So 3 could be anywhere, it not necessarily on that line, but can be in L.
No, but see, the collection of lines that we have taken is very restrictive, right?
Yes, sir. So it has to be on some line only.
Yeah, because again, one axiom we want is that given any 2 points, there must exist a line joining them, right?
Yes.
So there has to be a line joining 2 and 3. There has to be a line joining 1 and 3.
Okay.
Yeah.
So that pair 1, 3 and 1, 2 should be same.
1, not the pair. Not the pair. But the line joining these 2 points. So see, okay, let's go back to this guy. What did we say? There exists a line in L such that given any PQ, there exists a line such that PQ belong to L, right?
Yes.
So if I take my collection L to be this X, is this axiom satisfied?
Yes.
Yes, right? That's all we're looking for. But you see, now we've not made it very interesting. It's just one line. So everything lies on that one line. Yeah?
Yes, thank you, sir.
Okay. See, to sort of build on Keshav's question, let's look at the same set. Let's look at the same set 1, 2, 3. And let me draw it like this. So I have 1, I have 2, and I have 3. Can you think of a collection of, can you think of some L such that I can find 3 non-collinear points? Very good. There is at least one answer. Yes, Krishnendu? Hey, Krishnendu, sorry, your voice is not clear.
1, 2, 2, 3, and 1, 3.
Okay, very good. So I can take this to be 1, 2, 2, 3, and right. So I can take this to be my set 1, 2, 2, 3, 3. Just a sec. Right. Okay. So the point Keshav was trying to make is that when that okay, that's exactly what I was also trying to say. That's a good point. So basically, again, what I was trying to say and what Keshav was also trying to say is that if we take this L to be just X, there can be no non-collinear points. It doesn't matter how many points X has, right? X could have 3 points, 4 points, 10 points, countably many points, uncountably many points. It doesn't matter, right? See, for example, I could have taken X to be R2 as well. Okay. Now you see in 1, 2, 3, we can find something interesting. Yeah. But now if I take again in 1, 2, there are no choices that I have, right? There is only, even if I just restrict myself to the first axiom that I should find a line between any 2 points, then I'm stuck with L equals X. At least that much. So there is no third point, so there is no question of getting 3 non-collinear points. So because I want to make my geometry, since I want to make my life a little more interesting, let's make the assumption now that whatever sets we are working with, this has at least 3 points. Okay. So this has at least 3 points. So now let's look at, so the other axiom that we had so far is that there exists PQR in X such that PQR are non-collinear. So far from our experience, we have these two examples. Okay. So now we have this axiom A1, we have this axiom A2. Let's look at another example. So let's say I take X to be the set of all XY in R2 such that X squared plus Y squared is strictly less than. And for this collection, I take L intersected with X, where L is I'm going to write it like this, usual line in R. Okay. That means, so I'll draw the picture, but the first thing I want you to imagine is just close your eyes and try to see if you can think of this picture. So what am I taking? Picture that I'm taking is I'm taking the unit disk in R2 Okay. And the lines that I'm taking are, you take any line in R2 and you just intersect it with this unit test. Yeah. That is the collection of lines that I'm taking. And now what we need to understand, just take a moment to sort of think about it. I have these two axioms that I have defined, that we have come up with. Are these two axioms satisfied? Okay. So take 10 seconds, think about it, and let me know. What do you think? If you have an answer, please say it. So this is a good point to sort of stop with the first part of the lecture. So that is going to be the idea for the next two parts also, that we're going to keep developing axioms and we're going to keep testing it with these new models that we have. Okay. See, I've said this before, but I cannot say this enough. Thank you so much for curry leaf. And I would encourage everyone who is here, if they have not joined the Facebook page, or if they haven't subscribed to the YouTube channel, I would really encourage them to do so. The Curry Leaf team has done a fantastic job in organizing these lectures, and they will continue to do so. So all my wishes for their success. And of course, as an MTTS alumni, I'm also a part of Curry Leaf. So if you need any help, please let me know. And I really encourage everybody to join the Facebook page and subscribe to the YouTube channel. Right? Thank you, Curry Leaf.